It all begins from a single origin, a unique point in space and time. This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition, and lets scientists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text, and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all to help the lost find their way home. We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. This is the collective imagination, fueled by forward-looking technologies and the beginning of your most amazing discoveries yet to come.
Ladies and gentlemen, please welcome co-founder and CEO, Nvidia, Jensen Huang.
Nvidia builds computing technologies for the most demanding computer users in the world. We build it for you. Your work is done at such a gigantic scale. Your work so amazing, stakes so high, impact so great. Because your work has to be done within your lifetime. The computers you need are not the run-of-the-mill computers. You need a supercharged form of computing. We call it GPU accelerated computing. The GPU has become an essential instrument of your science, of your art, of your discoveries. And we think that the work you do are so amazing that we believe it's going to change the world. So we've dedicated our company to a singular craft. We've dedicated ourselves to advance the field that we're in a way that no company ever has, so that we could do amazing work Am I back there? We want to do our work so well so that you could do your work, so that you can do amazing things and change the world. GTC is about GPU computing. GTC is where the early adopters of GPU computing come to share your discoveries to reveal your innovations, to tell the world what amazing work you've done. GTC is getting bigger than ever, and it's accelerating. This year's GTC is twice as large as the GTC when we revealed Kepler in 2012. Now, the amazing thing is this. This is just a US GTC. Since 2012, we now do GTCs around the world. There's a GTC in Japan, which is coming up. We expect several thousand attendees to that. There's a GTC in Europe that will be starting this year. There's small GTCs happening all over the world. And yet, here in the United States, it's doubled in the last 4 years. The industries that come are broad and wide-ranging. And because of all the attendees, there are so many developers around the world now. In just 4 years' time, the number of developers of CUDA has increased by a factor of 4. But what's really amazing is this. Of the 300,000 CUDA developers in the world, the two that has grown the fastest, internet, hyperscale, and the automotive industry, hyperscale, internet, and auto, has increased by a factor of 10. There are now 300,000 developers around the world. And as a result, the number of high-performance computers that include GPUs is also growing incredibly fast. Supercomputing, high-performance computing, has doubled in just 2 years' time, from 2013 to 2015. In fact, 97% of all new high-performance computers, all new supercomputers, include NVIDIA's technology. I want to thank all of you for the support. I want to thank all of you for believing in NVIDIA. I want to thank all of you for adopting GPUs to do your work. Thank you very much. This is going to be the best GTC ever. And so let's get started. Today I'm going to talk about 5 things. First, I'm going to talk about a toolkit. Then I'm going to talk about VR. And then we're going to talk about deep learning, a deep learning chip, a deep learning box, and a deep learning car. We're going to talk a lot about deep learning, so let's get started. Today I'm excited to announce the Nvidia SDK. This is a unified toolkit, a unified SDK. The essential tools necessary, the essential libraries necessary for anybody who is doing GPU computing development. You know that one of the most important things we do in our company, building chips, of course, is one of them. Designing systems is another. Developing system software is very important to us. But one of our greatest investments, and one that I'm incredibly proud of, is the computational mathematicians in our company who are domain experts in their field, who are also experts in how GPUs work. That intersection between computational sciences and GPU architecture allows us to create new algorithms that are now embodied in libraries so that developers of all industries can take advantage of these tools to accelerate, to enhance, to make easy their work. There are so many different types of libraries in the NVIDIA SDK. Let me quickly go through some of them for you. The first one, of course, is the NVIDIA GameWorks. We love games, and we love graphics. Games and graphics has really pushed the boundaries of advanced computing for many, many years. For nearly 25 years, we've seen how quickly computer games has evolved and how hard it pushes technology. In fact, when I met Demis recently, and we were both talking at New York University, he came up to me and he said, "Hey, I'm a gamer," and he introduced himself. Demis introduced himself to me, not as an artificial intelligence research expert, but as a game developer. And he says he's known about our GPUs his whole life. And he's been a game developer and a gamer his whole life. And that's kind of how we started our relationship. GameWorks, amazing library, has physics, simulating the world is, of course, very, very important in the beginning of suspending you in disbelief. Creating a realistic world is the beginning of great games. Physics is an important part of it, simulating air, simulating water, simulating fire, simulating smoke, so that when you're in this environment, you feel that it's behaving in a real way. We got all kinds of new technologies that are now involved in GameWorks you can download pretty soon. Volumetric lighting, voxel accelerated ambient occlusion. Those little creases nooks and crannies in the geometries that you see around, all around you, with the little tiny shadows, that subtlety creates depth and it creates the nuance that convinces us what we're looking at is real. Trace shadows, hyperfresh from trace shadows, so that the shadows are softer as it goes further away from where you are. Okay, all of that's available now. NVIDIA DesignWorks. GameWorks is to make real-time graphics realistic. What DesignWorks is all about is making photoreal graphics. Iray is our physically simulated ray tracing system. It creates basically photorealistic images from computer designs. It is so vital in this particular field for us not just to create something that looks beautiful, but it has to be accurate, physically simulated, so that what's rendered is what you're actually going to see. What you render is what you see. We have a new library called MDL. It's a material description language, which embodies all of the complex mathematics of how surfaces react in an environment. Carbon fiber looks like carbon fiber. Brushed aluminum looks like brushed aluminum. Gold looks like gold, and gold paint looks like gold paint. Being able to capture the nuance and the complex mathematics of these materials is vital for us to recreate reality. Optics, not only do we use our own engines for our own ray tracer, like Iray, optics is essentially the CUDA, if you will, of graphics, of path tracing. This library accelerates path tracers, and we keep it open so that other people could develop their ray tracers on top of it. And then path rendering. When you look at scalable fonts in your text and how it's beautiful no matter what resolution you run it at, illustration has this property. When you zoom into it, it still remains beautiful. Those paths are rendered with computer graphics algorithms, and now we can accelerate it with the GPU. All kinds of new terrific tools that are in DesignWorks. ComputeWorks. CUDA is the computing architecture of our GPU. It is the reason why many of you have come to GTC. It has really revolutionized accelerated computing. It has democratized high-performance computing and made it available to every industry, every developer. CUDA is incredibly important to us. Whoop, I'm looking at the wrong slide. Here, I'll go here first. ComputeWorks. I'll come back to VRWorks and we'll go forward. On top of CUDA is a very important library called cuDNN. It's a deep neural net library. It's a linear algebra library that allows neural net developers to create their frameworks, their neural net architectures on top of our GPUs and have it run as fast as possible. cuDNN is one of the reasons why training networks on our GPUs is 10, 20 times faster than running on CPUs alone. Generated from supercomputing simulations. This week, we're announcing that CUDA 8, the next generation of CUDA 8, the next generation CUDA is coming. It supports our new GPU architecture with all of its architectural benefits. cuDNN5, even faster than cuDNN4, of course, and supports new features like long-term, short-term memory. NVGraph, as I've mentioned, and then index. Very quickly, I'll go back to VR. VR is an exciting new platform. And with every new platform, you enjoy graphics, in this particular case, in a very different way. You're suspended in that room, you're suspended in that environment. Because you're seeing the graphics so close to you, and because this graphics is moving with your head and with your body, any latency is going to cause you some amount of sickness. The latency, the performance, the interaction with the actual applications, incredibly important. We've created all kinds of new technologies for this new platform, and we're super delighted that they're integrated into head-mount displays by Oculus Rift, by HTC Vive, and it's also integrated into game engines like Epic, like Max Play and Unity Games. Amazing new experience. I'm going to talk a little bit more about that in just a moment. And then DriveWorks. DriveWorks is to our autonomous driving car computer what GameWorks is to GeForce. It's a suite of libraries, algorithms, that allows car developers or car startups or car platform developers to create self-driving cars. It is still in development. I'm going to give you an update today of some exciting things that we're working on, and hopefully announce something new. It's still in development, but they're accessible to some joint project laboratory partners, JPL partners. A handful of partners we're working very, very closely with. We treat them essentially like our own internal engineering team. The work, just like working among ourselves inside the company, is of course rather rough, but it gives them early access and gives them access to the market, time to market advantage of about a year. Early access program partners will be expanded to a larger handful, and we'll reveal that in Q2 of this year. And then general release will be Q1 of next year. We're working really, really hard in this area. Some really exciting developments that I'll share with you in just a moment. Autonomous machines. The smallest of embedded computers, the Jetson little one-chip computer, is the world's first embedded computer with deep learning capability. It has its own SDK and all of its tools because it's architecturally compatible with everything Nvidia. It's architecturally compatible with all of our suites. The software and the algorithms would work very naturally on this particular platform as well. Jetson is designed for autonomous machines, robots, cars, drones, that will in the future embed artificial intelligence, deep learning capability. Today, we're super excited to announce a new library for our platforms. It's called GIE, the GPU Inference Engine. Until now, it's been very clear that our GPUs are incredibly good at training networks. We could rip through images and train those networks with an enormous amount of data. We accelerate training by a factor of 10, by a factor of 20. We could take training runs that used to take weeks and reduce it down to days. However, one of the criticisms of our architecture has been that when it comes to inferencing, which is inferencing, classification, or the production part of the network, our performance is not as high. And the energy efficiency is not as high. Well, we changed all of that. There isn't something inherently counterintuitive relative to our architecture. It's simply we haven't created an engine for it. Where cuDNN is really designed for training, GIE is designed for inferencing. GIE is available today on our GPUs. And as a result, on TX1, Jetson TX1, the inferencing performance has increased from 4 images per second per watt to 24 images per second per watt. 24 images per second per watt is not only the most energy efficient, it's already the highest performance, but it's not only the highest performance, it's also now the most energy efficient. That level of energy efficiency makes CUDA unquestionably the highest performance and the most energy efficient approach to doing deep learning. Jetson TX1, 24 images per second per watt. So in just a little tiny computer, let's say that little tiny computer is 10 watts. 10-watt computer, 24 images per second per watt, gives you a sense of what you could do with inferencing in an embedded machine. Whether you're a robot or a drone, you can now look at images at a very high frame rate, infer information from it, and take the appropriate action. The Nvidia Jetpack with the GIE available in May. So, first announcement, the Nvidia SDK, the essential tool for GPU developers. GTC is about developers. Today, this is your first announcement, a toolkit for you. Now let's talk about VR. There's been a lot talked about in VR. VR is not just a new gadget. Just as your cell phone is not a new gadget. It's a brand new computing platform. When Nvidia was first started some 25 years ago, the LCD display had just come out. Prior to that, it was really CRTs. If it wasn't because of the LCD displays and making it possible for you to have thin displays, light displays, displays you can hang on the wall, computer graphics would never have been nearly as prolific as it has become. If it wasn't because of LCD displays, your mobile device wouldn't be nearly as useful as it has become. Because of those dynamics, the confluence of several factors has made it possible for virtual reality to happen, for virtual reality to become a reality. Head-mount displays are now light, the resolution is high, computer graphics performance is incredible. The combination of all of that is going to enable this new platform to allow new applications and new experiences to be possible. Now, we've already talked about video games. Video games is relatively clear. Who wouldn't want to be on the field of battle? Who wouldn't want to be running down the hall, chasing down monsters? All of those types of experiences are very natural, and you can imagine that extrapolation into VR. It's also very natural to imagine that VR would change how we design, experience products. Virtual design of cars, essentially a virtual showroom, so that you could look at your car design on a daily basis instead of after you create the clay from it. You could be literally standing next to that car. Architectural design, of course, very, very obvious things. But there's some things that are really kind of cool about VR that we're starting to think about. Now, of course, VR could take you to places that you can only dream of. Places that are too dangerous, for example. Places that are too far. Places that are beyond your ability to reach. Those kind of experiences are also possible in VR. Some of the things that I'm super excited about in the future of VR, how VR is going to transform communications. There was a demo that was recently done by Microsoft, their HoloLens. The HoloLens demo is really quite groundbreaking. If you haven't had a chance, take a look at it on the web. But basically, you can put on your head mount, put on your glasses, the HoloLens glasses, and you can be communicating, you can be talking to somebody who is very far away, and that person is literally standing in front of you. Science becomes a reality. Really, really amazing thing. Well, today, during this show, we're going to take you to some places that you probably only dreamed of and you can't imagine going. The first of that experience is Everest. Now, what we've done, and you can see this at the VR Village. What we've done is we've partnered with several really fantastic companies. So far, VR Studio, and the RVX, the effects studio, worked together with us to recreate the Mount Everest experience. Basically what's happened is we've taken 108 billion pixels of images, used a technology called photogrammetry to reconstruct Mount Everest, pixel by pixel, recreate it into 3D, 10 million polygons in this room, in this scene, and then use physics to simulate the swirling snow. All of that is going to be now displayed for you in real time. This is not a movie. In real time, in 3 full HD displays. Let's play for the team.
She has many names. To some, she is Sakamata, the goddess of the sky. To others, she is the apex experience, awe-inspiring, unforgiving, the pinnacle of human achievement. We know her as Everest.
Is that incredible, guys? That's great. Good job. So far, RVX, great partners. By the way, 108 billion pixels. That's the equivalent of 14,000 8-megapixel photographs on an iPhone 6. 14,000 camera shots came together in this computer program, reconstructed into 3D, and now you could navigate through it. Okay, so please go and enjoy that. Now that's a place that I can only dream of going. I can only dream of going, but I can imagine going. There are places where you can dream of going, and it's just not likely you're ever going to go. And so over the last several years, we've worked with engineers and scientists at NASA and Fusion VR to recreate meticulously Mars. Taking dozens of, photographs from dozens of satellite flybys of Mars. We've meticulously reconstructed the surface using photogrammetry. 8 square kilometers of the Mars surface has been recreated for your enjoyment. Rocks hand sculpted, 1 million of them placed in an informed way based on the satellite images. The design of the rover, the design of the habitat, the design of the spacesuit, all original designs from NASA. And working together, we recreated the Mars experience for your enjoyment here at GTC. It's going to be enjoyed for the very first time. Now, this environment is really quite amazing. The rover is physically simulated, so when it's bumping up and down the Mars terrain, it's reacting in a physically correct way. The lighting in the environment is wonderfully done, wonderfully rich. Global illumination is applied. High dynamic range is applied. There's even a lava tube. I understand that because of the gravity of Mars is only 1/3 of here on Earth. As the lava carves through the subterranean caves, it leaves these massive caves and they don't collapse. And these caves are absolutely huge. And you can only enjoy it by being in virtual reality. We could show it to you on screen, but it won't come near the grandeur that you will experience, that you're standing in front inside this cavern. Well, I guess the theory is that when we go to Mars, our habitats will be built in these caverns, these mile-long caverns, underground caves, so that we could be out of harm's way of radiation from space. Incredible, incredible recreation of Mars. Well, let me show it to you right now. Isn't that beautiful, you guys? Now imagine you're going to have head-mount displays in the VR village downstairs. You're now in the rover. Even the sound in the rover was recreated, or excuse me, recorded by driving the rovers at Johnson Space Center. Okay, so that this will just give you a sense of the experience you're about to have. Now, before we go any further, the question really is, if we were to send somebody to Mars, and we wanted to send an astronaut to Mars, who would we send? And who deserves the first ticket to Mars? And who would be more excited to be the first inhabitant of Mars? Well, when we think about it, there's only one adult childlike explorer who loves to do something nobody has ever done, wants to be first at everything. Ladies and gentlemen, Steve Wozniak. Steve.
Hi, Jensen.
How are you? I'm so excited.
Great to be here.
First of all, we recreated this. We recreated Mars, and engineers and scientists and artists have worked meticulously, painstakingly to recreate every detail. And now, after billions of dollars of R&D, we have now put ourselves in a position where we're ready to send one lucky astronaut. One lucky astronaut. And I heard an interview recently where you said that you would buy a ticket right off the bat for a one-way trip.
Absolutely. I've signed up for a few.
For a one-way trip. Now, you were the first to build, you built the world's first personal computer. You built the world's first a whole bunch of stuff, and in fact, you were part of a company called Fusion.io, and you built the world's first high-speed streaming storage, SSD, based on an SSD, so that we can have high-performance computing. And it turns out we're using a lot of that technology. You were first in a lot of things, and we thought that it would be great if you were the first to Mars, and this might be a one-way ticket.
I am totally honored, Jensen, and Nvidia makes it possible. Let's see. I haven't done it yet.
And so why do you want to go to Mars, first of all?
I don't know. It's just one of those extreme things. It's such an important step for humanity because it's so hard to do. It's so hard to get there. There are so many scientific obstacles that we have to overcome.
And what do you want to do when you get there?
Well, actually, whenever anybody gets there, I want to experience it in VR. I've been saying that for a long time now.
Now, if it was possible, I'm serious here. If it was actually possible to go, would you actually go?
Yes, I would.
You would? Uh-huh.
Yes, I would. Absolutely.
And when you get there, what would be your profession? What would you do? So you've been a computer architect.
Learning.
You've been a teacher.
Studying, learning, communicating what I saw, inspiring other people to want to go there, maybe escape Earth, global warming and all.
Okay. Well, I think that the first thing you should do when you land, and so I want to tell you this just as a favor for humanity. The first thing you should do when you land is please find Matt Damon.
I think the first thing I'm going to do, if it's live video streamed back to Earth, I'm going to use my feet and dig out the letters "Mom." Hi, Mom.
Ladies and gentlemen, the experience that Steve is about to have has actually never been done before, and I've not tried it yet, and I wanted to save that moment for Woz. So, Woz, why don't you go ahead and try it? Tell us how it is.
Whoa.
You look great.
Just a moment. Yes.
Oh, this is going to be big, you guys. You look great.
Supposedly I can maneuver myself. I picked up the controller backwards.
Are you familiar
I'm
with
walking
gaming?
around. Yeah, now I've got to find the rover, though. There's the rover. Whoa.
Now, ladies and
My
gentlemen,
God.
I have to say something.
Why do I feel weird? I feel weird, like I'm actually moving and getting dizzy. And I think I'll enter the rover. Now I'm in the rover, and I can spin it around a little. Whoa.
Now, all of this
gosh.
is made possible by our friends at Cisco. So, I contacted Ronan Trolla, who heads the Cisco telepresence. You know what? Look at what's happening here. I'm talking to Woz. His experience is actually being back to us, streamed back to us. Okay, so we're experiencing what he's experiencing from his VR glasses.
Wow.
All of this stuff, Roland and his team jumped on this, set all this stuff up for us, literally in a day. Literally in a day. So I want to thank Rowan, I want to thank Cisco, and yeah, really appreciate that.
And you won't believe the feelings when you do it.
On the ground, Scott Newman and the team, you guys are doing a fantastic job. It's amazing what you guys pulled off in just a day. Okay, hey, Woz, I'm going to go back to do my job and enjoy Mars. This is not a one-way ticket. When you find Damon, could you just let us know?
Okay.
Tell him we're looking for him.
Am I on Everest after global warming? Is that it?
You know, look, this is a trip to Mars. It's not a trip to Everest.
This is going to be incredible for whoever gets to really do it. I'm getting dizzy. I'm going to fall out of this chair.
Well, Woz, that was not a helpful comment.
Whoa.
All right, brother.
Can't thank you enough,
I'll let
Jensen,
you
for
know
this
when you can help me
opportunity.
again.
Oh my gosh, what NVIDIA has made possible.
All right,
Really?
you guys. Thanks a lot, Steve. Enjoy Mars. First astronaut on Mars. Okay, so virtual reality. In these examples, we're trying to make virtual reality as realistic as possible. However, in many different types of applications, for example, design, product design, architectural design, realistic is not enough. It's got to be real. It's got to be photoreal. And in that particular case, you need a whole new type of rendering technology. So the rendering technology that we were selling, they were running on a GeForce GTX Titan. That performance is really fantastic. However, that level of performance is simply not enough if you want to create something that is really photoreal. In order to create something photoreal, you have to follow photons as it bounces around the room, as it bounces through, as it goes through glass, as it refracts, as it picks up as the wavelength of the light changes when it interacts with different surfaces. All of that has to be physically simulated, or your eyes simply will not believe that what you're looking at something is photoreal. Now, in the case of design, it's utterly important. So, ladies and gentlemen, today we're announcing Iray VR. Iray VR. Nobody would think that it's possible. This is actually a stunt that I didn't think was possible. The idea that a supercomputer would be used to render a scene taking several hours. I mean, this is no different than Pixar rendering their film, and an entire supercomputer is used to compute each and every frame meticulously. And it takes days and days and days to eventually recreate that movie for final composition. This is no different. Here we're creating a scene, we're creating a room, but we have to create it in real time. Well, it turns out that ray tracing simply doesn't have the ability to do that. And so the team created a brand new technology. They basically rendered light probes throughout the area of the room that you would like to interact with. These light probes are basically entire light fields from that spot, how light would emanate from that spot. Each one of these probes is essentially a 4K render, And each one of these 4K renders takes approximately 1 hour on one box of 8 GPU server. 1 hour. We render 100 of these probes, which means 100 hours were dedicated to rendering the probes that go into this particular photorealistic room. Next, on a workstation with Quadro M6000, it needs to have a really, really large frame buffer so that all of these light probes could be resident in the frame buffer. We then rasterize the scene from the point of the eye to figure out the depth and which one of the light probes is the most appropriate to pick off the sample from, which is then mixed, filtered, processed, so that it looks appropriate from that eye. So that eye is picking up the information that was rendered from the combination of those 100 light probes. Okay? And so Quadro M6000 does the rasterization and does the composition. And then lastly, with very, very, very low latency, and all the work that we did with VRWorks and the integration into the head-mount displays and the integration into the engine, we can now allow you to enjoy VR in Iray. Now, Iray in VR. Now, the thing that's really, really, really amazing, it's just utterly beautiful. And it's something that you have to go enjoy. But I want you to be able to enjoy here. So let's take a look at this. So this is a head-mount display. What you're looking at is NVIDIA's new headquarters. And in fact, until this was done, until they did Iray VR, I had never been inside my building before. Now, this building is designed to be energy efficient. And so all the windows that you see in the ceiling is intended to let light in. But just enough light, and the angles of those triangles are designed so that during different times of the year, the light doesn't come into the building and heat up the interiors of the building, making it uncomfortable. And so we're trying to use as much natural lighting as possible. And so the rendering of this building and making sure that it's comfortable, well lit, and uses as little energy as possible is really important. And look at this. The polished concrete. I had never been in our building before. All of this is in real time, and it's in 3D. And the lighting is so beautiful. I think I'm going to go ahead and finish this building. 500,000 square feet. It's going to house somewhere between 2,000 to 3,000 NVIDIA employees. This is their phase one. And that is a building inside a building. It's the heart of the building. You come in through the center of that heart. You park underneath this building. We put all the cars underground because, here in Silicon Valley, our weather is really fantastic. And so no sense reserving all that wonderful climate just for cars. So we put all the cars underground, and eventually one of these days, all the cars will park by themselves. And so you'll just get out, and your car meanders down this ramp and finds a parking space and, future building. Okay? Iray VR, you guys, this is really incredible. 100 light probes now rendered on a workstation. Well, not too many people have supercomputers, though. Not too many people have supercomputers with Iray on it. You hit a button, it goes off and renders 100 light probes. It goes off and renders light field from 100 different positions. And then you put that on a workstation, you put that head-mount display on, and it's rasterizing in real time, and then recompositing from those 100 light probes to create this virtual reality environment. Well, this is going to be unbelievable for people who are doing architectural walkthroughs. It's going to be unbelievable for people who are designing cars, people who are doing serious projects. However, virtual reality has taken off everywhere, as you know. Cardboard, Google Cardboard, is being handed out to everybody. It was distributed by New York Times. It's available on Samsung Gear VR. It's going to be available on mobile devices all over the world. We want people to be able to enjoy VR irrespective of the computing device they have. And so one of the things that we're going to do, And this is really exciting. We made Iray VR Lite. This little brother of Iray. Basically, the way it works is this. It's not able to render the full 3D as beautifully as Iray VR. However, with just a press of a button, so long as you design in 3ds Max or Maya or whatever design tool that has Iray integrated, with just a press of a button, it creates a photosphere. And that photosphere is completely ray traced. That photosphere is completely ray traced. You download, your plugin, Iray plugin, or it's integrated, and then you download an Android viewer, and you grab yourself a cardboard box, the Google Cardboard, which is fantastically clever, or you get a ViewMaster with a phone stuck inside it. You download this app, and you now enjoy VR. We have this experience at the show floor. Give it a try. It's really, really fantastic. Iray VR. It's our second thing. So now let's talk about something really big. VR is going to be an incredibly big platform. I'm super excited about that. One of the biggest things that's ever happened to computer graphics, but one of the biggest things that's ever happened to computing. And I think we're going to realize, looking back, that this is one of the biggest things that's ever happened is AI. 5 years ago, the big bang of modern AI happened. Amazing AI computer scientists discovered new algorithms that made it possible to achieve levels of results and perception using this technique called deep learning that nobody had ever imagined. But the confluence of several things happened. The availability of lots of data that was labeled, and the availability of a processor called a GPU that was really abundantly used, abundantly available, came together and created the big bang of modern AI. Over the course of the last 5 years, so much development has happened. You have seen one announcement after another announcement, one article after another article, and there's so much to capture. But I think as we look back on 2015 is going to be a defining year for modern AI, and I argue for computer science, for computer industry, and very, very likely for all of humanity. That this year marked something quite special. That every year is a good year, but 2015 was a very special year. This year, something happened, and I selected a few to talk about. ImageNet, Microsoft and Google, using deep learning techniques, was able to recognize images better than a human for the very first time. A software program is able to perceive the world. A software program is able to perceive the world. A single algorithm was able to perceive the world better than any human. And then Microsoft took that level of accuracy and doubled it using a very super deep network. Whereas AlexNet was about 18 layers deep, their network was 180 layers deep. These networks are now so deep, it's able to pick up subtleties and nuances in images, and its ability to be accurate, unsurpassed now by any human. Superhuman levels of capability. But the thing that's really cool is it wasn't being trained. People are finding new application for it. It's not just images. Now researchers at Berkeley, at the Berkeley AI lab, was able to use the same deep learning algorithms, the same deep learning networks, combine it with reinforcement learning, and taught a robot how to control its own motor skills. Using simply a camera and 800,000 tries, this robot was able to fit a square peg in a square box. It's able to hang up clothes. It's able to screw a bottle cap on. Could you imagine writing a software program to do that? To screw on bottle caps? Well, it turns out that those programs, we haven't figured out how to write, but we have figured out one algorithm called deep learning that is now allowing robots to learn by themselves. The generality of this algorithm is quite fantastic. Baidu used the same network to train one network, 2 languages, English and Chinese. Deep learning has captured the imagination of so many people that it has gone pop culture. I don't remember the last time Rolling Stones wrote about computer science. Rolling Stones had a big spread on deep learning. on its implication of this new field. And of course, we can't overstate the achievement of Demis over at DeepMind and all of his researchers with AlphaGo. You simply can't overstate the importance of that. This is a simple game, 19 by 19 grid, 365 places you could place a stone, a black or a white stone, and the purpose of this game is deceivingly simple. Your objective is to surround the opponent's stone and capture that stone, or build a fence around an open territory and capture the territory. That's the only objective. However, the number of combination of moves, the number of board configurations is staggering to the mind. It's millions of times more complicated than chess, which has 16 pieces, 64 squares, and each one of the pieces have different constraints on them, so the possibilities of moves, the configurations of the board, is not nearly as complicated as Go. This 2,500-year-old game. And the year that Deep Blue beat Garry Kasparov on chess, physicists said that it will take another 100 years for a computer to master Go. That they thought it would take another 100 years, because the computational complexity of Go is practically infinite. It's practically infinite. And yet, this year, using deep learning algorithm, using reinforcement learning, Demis and his team created AlphaGo and took on the best living player of Go. Now, I think that is also just an incredible testament, because we understand what AlphaGo is the technology that has made AlphaGo possible. It's running on 1,000 CPUs, on 200 GPUs. It's trained on the moves and the board configurations of experts in history of Go. And then it played itself millions of times. It played itself millions of times, one game after another, as it discovered new strategies to win. And then Lee Sedol of Korea was able to challenge this computer and stay toe-to-toe. He ultimately lost 4-1, but I think it's just a celebration of his genius that a human could take on this supercomputer powered by deep learning, powered by AlphaGo, trained over millions of games, and to be able to take a game off of AlphaGo. Pretty amazing achievement by Lee Sedol. But what this says is that finally, computers powered by deep learning has the opportunity to do things that we can only dream of doing. That it can now develop algorithms. Now this algorithm can perform tasks that we can't actually imagine writing software for. Deep learning is no longer just a field. It's no longer just an app. It's no longer just an algorithm. I believe deep learning is way, way, way bigger than that. And it's one of the reasons why our company has gone all in on deep learning. You've heard me talk about deep learning now for about 5 years. And every single year, we do more and more in this area. We think this is so important. We think that this is going to utterly change computing. We think that this is a brand new computing model. Deep learning is a big deal. Now, the way to think about this is rather simple. Back in the good old days, we still do plenty of that today, domain experts, computer scientists would type commands into a box. We type commands into a box. Now, these commands are, of course, computer science is really, really a very finessed art. It is really quite broad. It's deep. Computer scientists, geniuses all over the world, they arguably, in the final analysis, type recipes into a box. Now, these recipes, of course, are really finessed, and they do amazing things. But they're ultimately written by domain experts. Each recipe, each dish is a different recipe. If you would like to have a computer program that looks at images, that's one program. If you have a computer program that would like to understand languages, a different domain expert would write a different program. If you would like to have somebody write a program that, for example, sorts a whole bunch of numbers, somebody would be a sorting expert and writes a different program. However, in deep learning, it's one general algorithm. There are many configurations of it. There are many different architectures of it, but in the final analysis, the basic approach is very similar. It's one of the reasons why the folks at Baidu with Deep Speech 2 was able to use exactly the same network to do two different languages. You didn't need a Chinese expert and an English expert to teach that network. It's the same expert. It's just one algorithm. And yet that algorithm could be used in Brett for motor skill detection and motor skill learning. And yet that same approach could be used for AlphaGo to learn how to play Go. And that same approach used by Demis and his team was the same approach that they used to play Atari games. Using one general architecture, one general algorithm, we're now able to tackle one problem after another problem after another problem. The fundamental difference is this. In the old traditional approach, programs were written by domain experts, and it took time. It took time and refinement. In this new approach, you have a general algorithm called deep learning, and what you need is massive amounts of data and a huge amount of high-performance computing horsepower. Fundamentally different approaches for developing software. The benefits are very, very clear. On the right-hand side, you see ImageNet. The blue dots are human-written feature detectors. These are computer vision experts that have dedicated their careers and their lives to detecting objects, detecting things using computer vision algorithms. And yet, researchers who are not experts in computer vision was able to design this architecture, this network, feed it with thousands and thousands of images, crunch it in hours and hours and days and weeks of high-performance computers powered by GPUs. And as a result, the results, as you can see, speaks for itself. It is now superhuman. This computing model has not gone, what is the phrase for that? Unnoticed by the industry. What started out in research, we had the good fortune of working with these amazing researchers on GPU computing all along, 5-6 years ago. But starting in research, it moved to technology platform providers who are now taking this basic approach and incorporating it into frameworks and engines. Companies like Facebook and Google, TensorFlow, Microsoft CNTK, Torch, Theano, Caffe. These frameworks are essentially the EDA tools of modern network design. It is the, if you will, EDA design tools that we use for designing chips. These are the EDA design tools, the environments for designing neural nets. Is essentially the tools, 3D authoring tools for designing neural nets. These frameworks are of vital importance to the development and the acceleration of AI. We work hard to put CUDA underneath every single one of them and accelerate each one of these frameworks to its limit. The library that we use to do that is called cuDNN. Beyond the core technology and frameworks, it's now moving into platforms. One of the most important things you're starting to see is AI as a platform. Amazon has AI as a platform. It's basically an operating system of AI. Voice recognition, image recognition, gesture recognition, so on and so forth. All of these services are now part of a cloud platform. Amazon has theirs, IBM has Watson, Google has theirs, and Microsoft has Azure. Cloud platforms in the future are going to be powered by AI. Startups are cropping up everywhere. Just yesterday, I think MetaMind was bought by Salesforce.com. DeepMind is now part of Google. The importance of AI can't be overstated. Great, cool startups are showing up everywhere. We understand there's some 1,000 startups. We're interacting with hundreds of them. $5 billion just last year invested in AI startups. This is the most important field, one of the VCs told me, the most important field that they're investing in today. And now it's going into industry. Just as web has, just as cloud computing has, just as mobile computing has. Started out in research, started out in core development, moved out into platforms, moved out into startups, adopted by large companies far and wide. The industries that are now looking into AI are the obvious and the not obvious. The obvious ones are the ones with millions and millions of customers. Retail companies, companies with a lot of data, company who needs to make sense out of a lot of data. Life sciences companies, medical research. Companies that you wouldn't have thought of, for example, IoT, they're going to be sensors connected all over the world. What GE calls the industrial internet is basically industrial internet connected to artificial intelligence. To be able to monitor elevators all over the world, power distribution systems all over the world, the smart grid. There's no way to write a single algorithm to understand how everything is behaving out there. Nothing is better than using an AI algorithm to monitor what's happening all over the world and to discover some insight to give you some early warning signs so that you can go take care of a piece of equipment that's about to fail. Industry after industry after industry, deep learning is now sweeping through them. Now, why is it that deep learning, after all of these years in AI, that deep learning is becoming such a large hammer? It's like Thor's hammer. It fell from the sky. It was like that big of a deal. Well, the reason for that is because deep learning, as wonderful and as beautiful as a concept as it is, and as much innovation that's still happening, it's a concept that's relatively easy to apply. You can actually use some of these frameworks that are being developed. TensorFlow, for example. You could use some of these frameworks that are being developed and develop your own, train your own network with the data that you have. Every organization in every single company should have the ability to use these frameworks to train their networks. The beauty of deep learning is that it's approachable, it's powerful enough, as you see, it's powerful enough to actually achieve superhuman results without superhumans to train them. Achieving superhuman results without superhumans to train them, without superhumans to code programs into them, is a big deal. It's one of the reasons why industry after industry analyst is now predicting that deep learning is going to be a very, very big industry. Now, I think that deep learning is not going to be an industry. Deep learning is going to be every industry. Deep learning is not going to be an application. Deep learning is going to be in every application. Deep learning is a brand new computing model. Analyst after analyst. However you think about it, they're big numbers. $40 billion by 2020 is one estimate. Over the next 10 years, $500 billion. John Kelly, my friend at IBM, head of Watson, they believe that cognitive computing, or discovering insight from IT, instead of just IT, discovering insight from IT, cognitive computing, will be a $2 trillion industry. It makes so much sense. Our goal is not to have computers. Our goal is not to be productive. Our goal is to have insight. Insight in business is more powerful than anything. We think this is going to be a big industry as well. And in fact, it's already our fastest growing business. It is starting to show up. After working on this for about 5 years, we've created 2 products that hyperscale companies can adopt and use in production. We call it Tesla M40 and Tesla M4. The Tesla M40 is intended for training. The Tesla M4 is intended for inferencing or production of that network. Now, Tesla M40, you could imagine, is quite a beast. Tesla M40 is a beast of a GPU accelerator for deep learning neural net training. And then we have this little cute thing here. This is the M4. And you put these in 1U machines. Every single rack of hyperscale computing can adopt this. Less than 50 watts. And as you heard earlier, because of GIE, our GPU inference engine, the GPU inferencing energy efficiency is off the charts. 20 images per second per watt. And so, as a result, there's just no reason to use FPGAs. There's no reason to design dedicated chips. This GPU is not only energy efficient from a perspective of classification and inferencing, it's also universal. If you wanted to do video transcoding, not a problem. If you want to do image processing, not a problem. All of those capabilities of these two GPUs, exactly the same. This one is designed to be as fast as possible, and this one is designed to be as energy efficient as possible. Tesla M40 and Tesla M4. These two products, since announcement, just earlier this year, has become our fastest growing businesses. And it's been adopted by internet service providers all over the world. Any company that has a large number of customers, large amount of data, large amount of content that they want to sort through and recommend, which is just about every internet company in the world, every internet service provider in the world, could really benefit from Tesla M4 and Tesla M40. We're super delighted with its progress, and there's now every evidence that deep learning is going to be a very large industry. It's not just research anymore. I think it's absolutely industrial, and it's going to be every industrial. Well, the thing that's really amazing is this. Deep learning so far has been using one basic approach. Largely, what is going into production is supervised learning, meaning you tell the computer what this thing is, and you train it to repeat it, to recognize it, to predict it in the future. And you keep telling it, you're wrong, and until one of these days it figures out what the right prediction is. This is an apple, this is a dog, this is a car. That approach of training is arguably quite laborious. And the reason for that is the vast majority of the world is not labeled. The vast majority of the world is not labeled. There are so many other things we like to do, and one of the most important things we like to do next is unsupervised learning. And this is from Jan LeCun's laboratory. They call it FAIR, Facebook AI Research. Jan and his team, Sumit Chintala, is doing work in unsupervised learning. And they're making really fantastic progress. This is using deep convolution, generative adversarial networks. That's a mouthful. That's a mouthful, okay? DC GAN, otherwise known, DC GAN. They made incredible progress, and the results are actually quite surprising. And basically what you do is you blast your network with a whole bunch of data. And this network eventually figures out what's important features. And so to show you an example of what we can do with that, Mike Houston, who heads up our AI work, yeah, Mike, why don't you stand up so they can just barely see you. Okay, there's Mike Houston. Mike is going to give us a demo of DC GAN, of Sumit's work out of FAIR. And I think the demo is coming up, right? Let's take a look at it.
So what you see here is we're pushing 20,000 images from the romanticism period through the network, and we're going to attempt to get it to learn how to generate these types of paintings on its own. So this isn't sort of the weird LSD trip type stuff that you've seen out of DeepMind. This is designed to actually effectively learn how to replicate these styles. So
okay, so first of all, we have tens of thousands of the 12,000, 10,000 images like this, of the same style?
That's right, 20,000 that are from the same art style, that's right.
And now we didn't label any of this stuff. We just simply took all this data and we shove it into this machine.
That's right. So it allows us to generate specific things. So for example, we can generate a landscape photo. So this is completely generated from the neural network based on what it's learned. So
now, Houston, let me just do this one thing. So we took these 20,000 images from the Romanticism era. We trained our network with it overnight. Now, after the network is trained, ladies and gentlemen, what's happening here is this. After this network is trained, what Mike is doing is he simply say, draw me a landscape. Now just think about this for a second, okay? Suppose you're a human, and I showed you all these images. And the next day, I say, draw me a landscape. And that's the landscape you draw. I mean, that's pretty amazing. This is a neural net. This is a computer. Apparently, it has artistic skills. It had figured out enough features of Romanticism landscapes that it can actually draw this landscape. Okay, go ahead.
So I'm partial to pastoral images, so we can also generate something that looks sort of like what you see on a farm with a nice big oak tree.
And so you guys type in farm. What did you type in just now?
So this is a combination, actually, of landscape and a forest.
Okay, landscape and forest, and boom, that thing shows up. Okay.
So, and we can do beaches.
And so you type in draw me a beach, and that's what shows up.
But what's actually even more powerful, because this is a generative network, we can actually combine things. So let's show you, let's say we want to take a sunset. We want to actually subtract out the fluffy clouds in it, and then add back in the beach. And then we actually end up getting a sunset at the beach. So this is the power of these generative models, is you can begin combining them together to say, give me something that looks a little bit more like that, less like that, take this, add this, subtract this. And it generates this on its own based on the generative models that it's learned.
Now remember, this network, in the final analysis, is still math. And so you could apply mathematics to this network and cause it to generate new images. I mean, this is really, really quite amazing. What a great piece of work. So anyway, Sumit and the guys over at Facebook did a great piece of work here. This is one of the early works that is done in unsupervised learning. And you guys know that this is how a lot of us learn. And because there's so much unlabeled data in the world, if we can crack this nut, if we can crack this, this is going to really, really accelerate the progress of network learning. Okay, unsupervised learning. Good job, you guys. Supervised learning, reinforcement learning. There's so many things to do. Transfer learning. Today, we take an enormous amount of computational horsepower to train the network. But in the future, you wouldn't want to be trained a priori. You want to be training almost all the time. And in fact, you might be looking at images, learn about it, right there in real time, and adapt your action accordingly. So what uses a supercomputer, we want larger and larger networks, more and more complex networks, more and more richer networks, and we want to train it with more and more data. We want to be training it with almost real-time data. So these supercomputers that are now being used needs to be way, way bigger. On the other hand, we would like to do deep learning in real time. We would like that autonomous machine, that robot, to literally be studying all the time and reinforcing its network, learning in real time. For example, the Brett robot is thinking in real time. And so the amount of computation it does isn't just about recognizing the image. It has to figure out how to recognize the image and apply its motor skills repeatedly to figure out the proper action. We simply don't have enough computing horsepower. 3 years ago, we dedicated ourselves on the single greatest endeavor in the history of our company. We decided to be all in on AI. We decided to be all in on HPC. That for the first time, we would design a GPU architecture that is dedicated to this field of work, dedicated to accelerating AI, dedicated to accelerating deep learning. And to do it, create it in a form factor, in an architecture that is perfect for high-performance computing. Several years ago, thousands of engineers got together. Approximately $2 to $3 billion of R&D later, we have built the most advanced processor, the most advanced GPU that I think anyone has ever undertaken. Ladies and gentlemen, the work of thousands of engineers, the most ambitious project we have ever undertaken, the Tesla P100. This processor is utterly amazing. The processor itself is over 15 billion transistors. 15 billion transistors. It is the largest chip that has ever been made. But it's housed on chips stacked on top of chips in the 3D stacking technology. And altogether, this module is 150 billion transistors. Now, just to put in perspective, what I was holding up just now, what was called GM200 internally, the Maxwell, the high-end Maxwell, 7 billion transistors. 150 billion transistors on this module. The odds of it working at all is approximately 0. 150 billion transistors, 5.3 teraflops, 64-bit double precision, 10.6 teraflops, 32-bit precision. And one thing that we did that I'm so delighted about, adding new features and new architectures and new instruction set formats for deep learning, 16-bit performance, 21.2 teraflops. Not only that, we increased the size of the memory internally. The amount of data that's coming through, pumping through our chip is so great because we're processing it so fast. 14 megabytes of shared memory register files. These are register files. This isn't an L2 cache. This is a register file. 14 megabytes of register files with an aggregate throughput of 80 terabytes per second on the chip. Utterly amazing numbers, amazing throughput, and on top of that, it has a 4 megabyte L2 cache. The Tesla P100, ladies and gentlemen. The thing that's really, really amazing about the P100 is that when we first started working on it, we have rules in our company. And in order to be successful in execution repeatedly, once after another, you have to be thoughtful about the amount of risk you take. And the reason for that isn't because you don't want to take one giant leap, and the reason for that is because by taking a lot of leaps over a long period of time, it is the best way to stand on the shoulder of giants. However, because this is such an incredible endeavor and we're changing so many things, so many new pieces of technology have to come together. We have a rule inside the company. No great project should ever endeavor 3 miracles. No project, no box, no chip, no effort should have to rely on 3 miracles. The Tesla P100 is 5 miracles. 5 miracles. First of all, the Pascal architecture. You guys saw some of the stats. This is also our first unified memory. So CPU and GPUs for many programmers in the audience. This is just it's got to be, wow, Christmas in April. Okay, this is so great. Unified memory, CPU and GPU can share memory. Preemption, such a vital thing for a first-class computing processor. Now we can run very, very long programs and preempt the GPU. Preempting thousands of processors is no easy task. Preempting one processor is not so hard. Preempting thousands and thousands of processors at the same time, incredibly hard. Well, that technology has taken us a very long time to invent. Ladies and gentlemen, Pascal has preemption. I am so freaking excited about it. Are you allowed to say that on stage? That's how of a big miracle it is. Not to mention all the deep learning algorithms that it encapsulates. This processor has so many transistors, it runs so fast that unless we can figure out a way to reduce the voltage all the way to nothing, you simply are not going to be able to make this processor run at all. So we use FinFET technology. This is the world's largest FinFET chip that has ever been done. 600 millimeters squared. If I were holding it up right now, you could see it from the back row. This chip is huge. 15 billion transistors, incredible amounts of memory, all in FinFET, 3-dimensional transistors. Not only are the gates 3-dimensional, not only are the transistors 3-dimensional, the chip itself is 3-dimensional and is stacked on top of other 3-dimensional chips. It's chip on wafer on substrate. The largest CoWoS chip that has ever been made. Integrated with HBM2, the fastest memory ever been made. There are 4,000 wires. 4,000 wires. Maxwell has 384. There are 4,000 wires that connect Pascal to all the memories around it. The processor is so fast, and we wanted it to be even faster. We wanted to create a multi-GPU configuration. That is the fastest you can imagine. And the processor is so fast, the communications between them, because they have to synchronize information, has to be just as fast. So we created a brand new interconnect called NVLink. 160 gigabytes per second. 5 times the speed, aggregate bidirectional speed of PCI Express. These miracles, every single one of them, are the first of its kind, and surely the first of its kind for us. Several thousand engineers worked all over the world together to bring it all together. And yet there was one miracle that we had no control. Well, I would say we have no control over any of these miracles. So many of this requires the partnership of great companies all over the world. TSMC, Samsung on the memories. Right? So many people were involved in this project. And the last miracle, we went all in on a brand new GPU architecture. But unless great AI engineers and great AI scientists were able to create new algorithms that could take advantage of it, we have just created the world's most expensive brick. And so this is such an important thing. 3 years ago, when we went all in, it was simply hope and faith that if we don't build it, they can't come. But if we built it, they might not come. And that, I think, is the courage of innovation. That is one of the things that I'm most proud of NVIDIA, the fact that we are willing to go all in on something, on sheer belief, with so much uncertainty. These 5 miracles came together. The odds of any of the miracles happening was relatively low. When you compound it into one project, it is practically zero. And yet, ladies and gentlemen, I can tell you, Pascal P100, it is in volume production today. We took giant leaps in just about everything. Compute, bandwidth, GPU compute. And we've been working with developers all over the world, pioneers who are working with us, advising us along the way. And they just saying amazing things. Jan LeCun says GPU acceleration has accelerated the progress of AI. And we need more GPU, more memory, more bandwidth, and Pascal is the ticket. John Kelly said this is a new era of computing. Andrew Ng says AI computers are like space rockets. The bigger the better. Pascal's throughput interconnect will make the biggest rocket we've seen yet. And Microsoft is developing not just a 158-layer network, they're developing a 1,000-layer network. Servers are being built by OEMs all over the world now. IBM Enterprise, Hewlett-Packard Enterprise, Dell, and Cray. They all have samples. They're building their servers. They will probably announce it in Q4. They'll ship it in Q1. However, between now and then, hyperscale companies all over the world are going to consume everything we can make of Tesla P100s. We are in production now. We'll ship it soon. And it will show up in the cloud first, and then by OEMs in Q1. So, ladies and gentlemen, Tesla P100. Our strategy is to accelerate deep learning everywhere, for every platform, for every market, for every single industry. First, accelerating the cloud. The cloud is the fastest, the best way, the early adopters of deep learning, and bring this technology to users all over the world. However, there are many companies that need to have resident on-premise computing. And our OEM partners will take deep learning accelerated servers all over the world on our behalf. We have it in the cloud. We now have OEM servers for IT. However, there's still some users that would like to have access to deep learning that this is simply not fast enough. They would like to have the fastest, the latest technology. They would like to have it integrated. They would like to make sure that all the software is working perfectly and tuned and fully accelerated. The frameworks that they will use will be of all different types. And they are the early adopters. They're the data scientists. They're the researchers. And they need something now. So we decided to build the most advanced computer that anyone has ever built. We decided to build the Nvidia DGX-1, the world's first deep learning supercomputer. It is engineered top to bottom for deep learning. It's 170 teraflops in a box. On a rack, it's 2 petaflops. A 2 petaflops computer for deep learning has 8 GPUs, 8 Tesla P100s, organized in a hybrid cube mesh. It accelerates all the major AI frameworks. Let's take a look inside. The densest computing node ever made. 3,200 watts. 8 GPUs. A blanked out screen. Organized in a hybrid cube mesh. Getting data in and out of this machine, because it processes data so fast, is vitally important. And so we have 7 terabytes of streaming SSDs. We have quad InfiniBand and dual 10 gigabit Ethernet. Connected together, this is one beast of a machine. One single node, 170 teraflop machine, the densest computer ever made. Incredible, incredible. Now let me compare it to something that is available every day. A dual Xeon processor, for example, if we added up all the flops between CPU and GPU, is about 3 teraflops. The total amount of aggregate bandwidth that's inside connecting processors is 76 gigabytes per second, which is basically the QPI link. It takes 150 hours for a server. 150 hours. 150 hours. Basically almost 2 weeks to train AlexNet. So if you had a server, it takes almost 2 weeks to train, 150 hours. DGX-1, 170 teraflops in one box. 768 gigabytes per second of aggregate bandwidth connecting the processors to each other. And if you wanted to train AlexNet, it's not 2 weeks. It's 2 hours. 2 hours to train AlexNet. 2 hours to train a network. Now, the part that's really quite shocking is this. Because when you scale out using traditional off-the-shelf high-performance computing architectures, the interconnect, the communications between the processors becomes such a large burden as you synchronize the nodes. Each additional node that you add gives you diminishing results. And over time, as you scale out, the speed up is no longer great. It would take over 250 nodes, to keep up with one DGX-1. Over 250 nodes to keep up with one DGX-1. Unbelievable. It's like having a data center in a box. 250 servers in a box. Last year, I predicted that 1 year from now, because I realized that I had already realized that we're all in on Pascal, that we were all in on NVLink, that we were all in on the miracles I talked about, that 1 year later, I expect to see a 10x speed up. A 10x speed up year over year. Well, ladies and gentlemen, I'm delighted to announce that we achieved a 12x speed up year over year. The fastest computer in the world for deep learning at the time was 4 Maxwell GPUs. At GTC 2015, we were so proud. We were rightfully proud to announce that we could train a network that used to take a month and now do it literally in 25 hours in one day. Today, we can now do it in 2 hours. 1.33 billion images per day. This particular machine just cranks through it. Now imagine you're a researcher. Your work is so important. Your need to discover the next big thing so great. The stakes of your work so great. The laboratory filled with amazing engineers. The world's best of its kind, trying to do a deep neural net design. How could it be possible that you can tolerate the training times necessary, the training times that would take days and weeks and months? They need the fastest supercomputer in the world at their fingertips. And that's why we built the Nvidia DGX-1. 12 times speed up year over year. Well, there's so much more to DGX-1. The thing that is important isn't just the fact that we built something super fast, something super cool, but the architecture of it has to enable new types of applications. And one of my heroes, somebody who, before anybody talked about deep learning, before anybody else was talking about the importance of this new computing model, a researcher was explaining all of this to me in languages that I understood, explaining to me the impact of this work. Brian Catanzaro, where are you? Where's Brian? Brian Catanzaro is researcher at Baidu. He was formerly one of NVIDIA's greatest researchers. He was one of the reasons why NVIDIA got into this whole business in the first place. And you're my hero. I just want to tell you that. I hope it doesn't embarrass you. And
well, I am thoroughly embarrassed at this point.
not only are you graceful, gracious, and just an utterly brilliant researcher. Very few people in the world knows as much about deep learning and the intersection of deep learning and GPUs, because he knows so much about GPUs. And today I invited Brian to come and share with you some of the research that he's doing. And would you like a little clicker?
Sure. Thanks.
Brian's going to tell you about just a little bit about the work that he's doing on Pascal.
Great. So at Baidu, we're really excited about being able to use Pascal and NVLink to accelerate the training of our recurrent neural networks. And I wanted to mention a little bit about what a recurrent neural network is. So convolutional neural networks are often used for processing images and video. At Baidu, we care a lot about sequential data, text, and speech. And I think these are really useful for many different kinds of AI problems. Recurrent neural networks have a time series dependence. They operate on time series data, and then they produce a time series output. So for example, in speech recognition, we operate on an input waveform that's sequential samples taken as time goes on, and then we produce a sequence of characters that represents what the user said. So this sequential dependence is the power of RNN because it gives it memory and it gives it the ability to understand the dependencies in the data, which are very interesting. But it also makes the parallelization of the training process more difficult. There are two major ways of parallelizing the neural network training process. One of them we call model parallelism, is basically where you take a look at your model and you realize, wow, there's so many neurons here, I could partition them and assign them to different processors. Say, for example, I'll put half of them on GPU 0 and half of them on GPU number 1. And then the other kind of parallelism is called data parallelism, where we realize, hey, our training set huge. It has thousands and thousands of hours of audio data, for example. I bet we could chop that up in pieces and then assign different pieces to different processors. We have been trying to use model parallelism for many years, on and off, for different applications, and it's always been difficult because of several things, one of them being the interconnect between processors. And so Pascal is going to really help out in that regard. Not only is each GPU much bigger and much faster, which we really need, but the interconnect between GPUs is much better and has it's faster, and it also has new capabilities that we're going to use for interesting things. And I wanted to give you sort of a sneak peek at some of the things that we're thinking about doing with these new capabilities. We've been working on a project for a while called persistent RNNs. And the idea behind persistent RNNs is that since the weights are reused over multiple time steps as the model iterates sequentially over the data, we can actually keep those on chip, keep those persistent in the register file of the chip, and then do all of the math without needing to talk to memory nearly as much. And the advantage of this is that we can reduce the number of training examples that are required to keep our GPU busy. So instead of needing 64 examples to keep the GPU busy, we can keep it busy with, say, 8, and running very close to peak efficiency. Now, the big limitation of persistent RNNs is that we need to fit the entire weight matrix on chip in the register file. And so on Pascal, it was about a 6 megabyte register file. On Maxwell is about a 6 megabyte register file. On Pascal, you just saw it was 14. So that's a big leap that's going to help us. But the thing that's even more exciting to me is that NVLink is going to allow us to use model parallelism as well. So we can take that matrix and partition it across the register files of multiple GPUs and use the synchronization capabilities that NVLink provides in order to very efficiently communicate between those GPUs and train our model. So when we combine this style of model parallelism with persistent RNNs with data parallelism, since we need fewer examples per model to keep the GPUs full, we can actually use more copies of the model and use wider data parallelism. That's going to combine to allow us to scale to even more processors. And I think we're going to be able to go quite a bit larger than we've ever been able to in the past, like 30x bigger. I also wanted to point out that my colleague Greg Diamos, who's been doing most of the work on persistent RNNs, is going to be presenting on Thursday. So if you're interested in learning more about this topic, I'd recommend going to see his talk. But just to summarize, we're really excited about the possibilities that NVLink and Pascal give us to strong scale our RNN training. We think it's going to make huge progress in our AI applications that rely on RNNs because we'll be able to churn through far more data far more rapidly.
That's really awesome. Thank you very much. Brian? You should be a professor.
Thanks.
30 times bigger model. 30 times bigger model. That's the benefit of Pascal and the benefit of the new architecture in NVLink. The next speaker has made a contribution that is just absolutely gigantic. Absolutely gigantic. You know, one of the things I mentioned earlier, these frameworks, the frameworks, are basically the design tools of modern AI. By encapsulating all of the complexity into a nice and easy to use framework so that anybody can design new networks is really important. But more than that, the folks at Google and TensorFlow, Google TensorFlow, open source TensorFlow. They made one of the most important new tools available to everybody for free. It's completely open. On GitHub, it has the most number of likes of contributors and users than any other open source tool. 20,000 likes. And you know how critical engineers can be. 20,000 likes. This tool is being used far and wide now, TensorFlow. It's completely open sourced. And I really believe that this is going to democratize AI. TensorFlow is going to has the opportunity to move a high quality tool that has been optimized for modern computing environments and making it available for every industry, every developer, every researcher, so that we can accelerate the progress of AI. I first learned about TensorFlow watching a talk by Raja Manga, and I thought we'd invite Raja to come on stage and tell you a little bit about it. Raja, why don't you come up and tell us about your important work? Ladies and gentlemen, Raja Manga.
Thank you, Jensen.
First of all, congratulations on TensorFlow.
Thank you.
My goodness, I mean, you guys literally launched this just several weeks ago, and it's just swept through the industry.
It's been great. The community uptake has been great. Everybody seems to love it, and we are really invested in making sure it continues to be even better.
Mm-hmm. And then what is the reason why you guys, well, first of all, you guys developed this tool for your own internal development. And,
That's right.
and the thing that I saw in your presentation, which I thought was really great, is you said that inside Google, in just 1 year's time, and there was a chart that you were showing, was on an exponential growth.
Yep.
Like there's currently some over 1,200 applications, from what I can count, that are now basically AI accelerated, deep learning powered, and just a year ago was only 400. I mean, how is TensorFlow must have been a vital part of all of the developers inside Google picking it up.
Right, so the tooling definitely makes it easier. You know, we've invested a lot at Google in tooling to make sure that the developers and the researchers can really take what they want to do and scale it up. And now, you know, it's really expanding to many, many different applications and projects.
Now, for the developers that are currently using TensorFlow, what do they love most about it?
So for a lot of the developers, they really want to express all kinds of new things. You know, if you have researchers who want to try out new ideas, like the RNN stuff that Brian just talked about, or convolutional nets, or over the last year or two, there's this whole thing about batch normalization. So there are a lot of new techniques around these algorithms that developers want to talk about. And with TensorFlow, we've tried to make that really, really easy and allow them to still scale it up.
And it doesn't matter what data set it is, right? It could be a motor skill data set. I could use it to train a robot.
Exactly.
Mm-hmm. And so whether it's robot or voice or images or whatever we come up with, it could be you know, seismic data for all we care. I mean, just whatever data that data science would like to use to train a network and apply that network in production, that's what ultimately TensorFlow is for.
That's right.
Yeah. The thing that's really, really cool is you guys open sourced it. And because you open sourced it, it made it possible for our engineers democratized high performance computing. But what TensorFlow is going to do is you're going to democratize deep learning. And I think that's a huge, huge contribution to humanity and to computer science. I want to congratulate you.
Thank you.
All right, thanks a lot, Roger.
Thank you.
And by the way, we love working with you guys. You're good. You're good seed. Great guys. Okay, so TensorFlow, you saw that all the OEMs from HP to IBM, Cray, Dell will have high performance computing servers built. You saw that Baidu is doing amazing work. Brian and his team is doing amazing work to advance artificial intelligence and the scale out of deep learning. And you just heard from Raja the important thing of TensorFlow and its vision of democratizing AI. All of that is what we intend to do with DGX-1. That is our purpose with DGX-1, the world's first deep learning supercomputer, fully integrated, the single highest performance one node, would take 250,000 servers. And if you just did some quick math, 250 servers at $10,000 a piece, $2.5, $4, $5 million, depending on the price that you usually pay, just to interconnect between the servers will be more than $500,000, just to interconnect between the servers. DGX-1, $129,000. We're announcing that today you can go to nvidia.com/DGX1 and place your order. Super excited about DGX-1. Well, the question is, who should get it first? Well, the people who should get it first are the pioneers of AI. The pioneers of AI. Berkeley, CMU, MIT, NYU, Stanford, Montreal, Oxford, Toronto, the Swiss AI lab. These are the pioneers of AI, and we have chosen them to be the first recipients of the first DGX-1s that come off the line. We want to make sure that the future of AI continues to run at the speed of light, and that we put the right instruments, the best instruments, in front of the world's most daring researchers. Super excited about that, and today we're announcing that they're going to get the first ones. They have been awarded as part of our Pioneers in AI Research. I'm also super happy today to announce something very special, that NVIDIA is the founding technology partner of MGH's Center of Clinical Data Sciences. As you know, Mass General is the US's leading research hospital. They have the largest depository of patient data in the world. Pathology, radiology, genomics data. Using DGX-1 and using deep learning, their scientists, our engineers, are going to work together to advance medicine. This is really, really exciting stuff. If there is one application where a lot of data is available, a lot of very complicated data, very messy data, very unstructured data is available, it is in the field of medicine. And what better application for deep learning than to improve our health, improve life? Deep learning for medicine. Today, we're announcing our partnership with Mass General. So, our strategy for Tesla. You heard today about deep learning. There are so many ways to bring deep learning to the world, and we're going to, our strategy is to bring deep learning to the world in every possible way. Tesla M40 and M4 will be for hyperscale cloud data centers. K80 will be for multi-app HPC. If you have a research organization and you're going to be running fluid dynamics or molecular dynamics as well as deep learning, then the perfect GPU for you is K80. It has double precision, has single precision, has wonderful deep learning capability. If you would like to build a high-performance computer that scales, strong scaling, as Brian was talking about, where weak scaling is simply not an alternative, that strong scaling is essential, Tesla P100 is your answer. Powered by NVLink, powered by the new Pascal architecture, it is the best high-performance processor for strong scaling. And then lastly, if you would like to get a fully integrated box, you are one of the early adopters. You want to jump on deep learning. You're a data scientist, and the last thing you want to do is maintain and build and maintain a high-performance computer. DGX-1 is your answer. The highest performance computer in a single node, the world's first deep learning supercomputer. Irrespective of which platform, irrespective of how you would like to enjoy deep learning, the computer infrastructure is now available to you. And now with algorithm work that you're seeing around the world, with wonderful frameworks like TensorFlow, deep learning has been democratized. The Tesla family, deep learning everywhere. Let me talk about one more thing. The last thing is deep learning for cars. Well, if it was an amazing year for AI, it's also an amazing year for cars. There are just so many announcements. The fact of the matter is, we all know this. AI is coming to cars. AI is coming to cars. When we thought about helping to create self-driving cars in the beginning, the basic approach was sense, plan, act, using traditional computer architectures, using traditional computing techniques. We're going to continue to do that as well. We're going to continue to do sense, plan, act. The basic loops of self-driving cars is know where you are in the world, figure it, based on a map, also based on your senses, localize. You see what's around you, and then you act. Plan, sense, plan, act. The basic loop of robotics. So we decided to build a computer dedicated for that very functionality. We built the world's first AI car computer. It's called the Nvidia Drive. Our basic approach was this. We would build an end-to-end computing platform, all the way from training the network that would ultimately run in your car. Training the network is the beginning, training your network for your car. as you've heard from all of the leaders, training your network is the first step of having an autonomous driving car. And so we've created a platform that allows you to train on any framework you would like to use. Caffe, CNTX, CNTK that is, excuse me, TensorFlow, Theano, Torch, you name it. Training your network. And then taking that exact same network, running on something that has incredibly high performance, but is also very high energy efficiency. As I mentioned today with GIE, you could take that network and run it on a car computer. We call that car computer the Nvidia Drive PX. It's the world's first deep learning car computing platform. It's scalable. We believe that AI will be used for car computing, not just for autonomous driving. AI will be used to talk to you. You will give it commands. It'll be looking around in your smart mirrors. Your car will be able to see all around you and tell you there's a bicyclist on your right. Of course, it's going to avoid it anyways, but it's going to tell you. You could talk to it. You could change temperatures. Looking at your gesture inside the car, it could tell when you're dozing off. It could tell whether you're looking in the direction of the oncoming traffic. AI will be used inside the car. AI will be used to drive the car. AI will be used to keep you out of harm's way. We believe AI will be used across the board in car computers. We used one architecture from infotainment to cluster, to ADAS, to self-driving, all the way to mapping. It's a completely open platform. All the APIs are available to everybody. Now, the last time I showed you, we had started working on object recognition for our Drive computer. The thing that's really amazing is only in just a few months, after a great deal of effort, our scientists, our researchers working on our network has now achieved the #1 score on the CUDA benchmark. This is the self-driving benchmark. I'm super proud of them for doing this. We have the #1 accuracy on CUDA. The thing that's really great is that #2, #3, #4, #5, #6, #7, #8, all GPU accelerated. Working with a large community of researchers that are trying to develop self-driving cars, we're open to work with everybody. We want to encourage everybody to enable this capability so we can make streets safer, so we make driving better, and hopefully it might even change the way we design our cities. Well, let's take a look. Let's take a look at what it can do. Okay, so not only is it accurate, as I mentioned earlier, GIE also makes our network running on our processor super fast. And so we're detecting cars in the front on the upper right, in the back, or no, in front in the upper left, behind you in the upper right, but also in your side mirrors. So the thing that's really cool is that you could detect objects all around you using exactly the same network. And all of that is running on this little tiny processor, the smallest version of Drive PX. This is the smallest version of Drive PX. 180 frames per second, 180 frames per second, detecting cars all around you. Now we can detect lanes, we can detect signs, we can detect anything we wanted to train it to do. And that's really the wonderful thing. That's the beautiful thing about a deep neural network. Whatever you train it to do, it will do. Whatever you train it to detect, it will detect. Okay, so Drive PX. Well, the next thing we like to do, so that's an update on perception. We like to also make sure that you can map. Well, if you want to figure out exactly how to drive and drive safely, you want to have as much information as you possibly can. This is called HD mapping. You could use LiDAR, but we also believe that you ought to use LiDAR and camera and everything that you have. And the cameras will use photogrammetry, basically motion photogrammetry, to do basically what is called structure for motion, to create and identify important points in the surrounding and map and reconstruct a 3D world for you. Okay, that mapping is called high definition mapping, and we've created a platform that allows us to do that. Let's take a look at that. Oh, can we? Well, I think I just leaked that out the door. Okay, excuse the sequence. So Baidu, Andrew Ng and his lab, as you guys know, are working on a self-driving car. And he was so enthusiastic about it, he asked me to share this with you guys. The thing that's really important is this. While you're creating a self-driving car, you've got all kinds of algorithms that you want to deploy onto it. You have sensors and cameras all over your car. what kind of computer would you need? Well, it turns out they need a GPU-accelerated supercomputer. And before the existence of Drive PX2, they had to build their own. They had to build their own. But they have wonderful computer scientists, they have wonderful computer engineers, and they built a cluster, a supercomputing cluster that fits in the trunk of a car. Now, this isn't something that every car company can do, and this isn't something that every car company wants to do. And so the thing that we did was we took all of that supercomputing horsepower and we shrunk it into one platform we call Drive PX2. Drive PX2 has 2 Tegra processors on it, and it has 2 Pascal next generation GPUs that hasn't been announced on it. And so if you take a picture of that and you zoom in carefully, which I know you guys will do, you do it to me all the time. Let's see, hang on a second. I took the serial numbers off. Okay, and so this 4-chip solution, whereas you were looking at a 1-chip solution just now, this 4-chip configuration of the architecture would allow you to basically have a supercomputing cluster inside cars. You connect 12 cameras to it, connect it to your CAN bus, and you can be doing photogrammetry, motion photogrammetry, as well as collecting information from LiDAR, fusing it, in real time computing the map, and instead of streaming up to your cloud 12 high-definition video streams, you stream up to your cloud point clouds that are highly compressed, and that will be accumulated in the cloud over time, crowdsourced by all these cars that are driving around, registered in the cloud to create one big high-definition map. And so this particular platform we are announcing today will also be a mapping platform. The car computer will be Drive PX2. The computer that's in the cloud will be DGX-1. End-to-end, exactly the same architecture. PX2 in the car, DGX-1 in the cloud. Let's take a look at real-time mapping. So basically what's happening here is that this car, our car, this is using 4 cameras. It's able to detect up to 15,000 important points. It selects 15,000 important points per frame, per second, per camera. And so altogether, the 4 cameras can collect up to 1.8 million points per second. 1.8 million points per second. The points are not only in 3D space, but it is also in color. And so we would accumulate all this information, and we would load it up into the sky, and that would be then registered and calibrated and maintained using DGX-1. Okay? So this is mapping. We created this platform so that every mapping company in the world could have the benefit of mapping cars. Building these car computers for mapping it's a really expensive endeavor. You're basically creating a supercomputer that fits into the trunk of a car. But we've now, with Drive PX2, with DGX-1, have created an end-to-end computing platform that car computers can use, mapping companies can use. And we have to map the world before all the cars can safely travel around the world. Driving. I want to share with you something that's really new. Just now I talked about how, in fact, we can drive by sensing, by planning, and then by acting. Where are you? What's around you? Figuring out what path to take. It's a mathematical problem. It's a path planning problem. And then lastly, take the action of driving. Well, we've been working for some time in creating an alternative approach to doing that. A little bit like what Brett, the robot, was doing. It learned by itself using deep learning and to figure out what actions it has to take. It didn't detect bottles, it didn't detect caps, it didn't detect bricks. It wasn't taught to do that. It simply taught, what is it that I have to detect? What action do I have to take? Basically an end-to-end approach to training networks. We've been working on a project that's really, really super fun. The name of the car is BB-8. We have 3 cars. You're going to see BB-8 today, and you know BB-8 has friends, R2-D2 and C-3PO. And the name of the network is a brand new network that we created called DaveNet. This network is very different than the network that you just saw. The other network was detecting objects. This network is simply going to drive. And it's so cute. You're going to see BB-8 learn how to drive. And today we'd like to share with you our progress on developing the first self-driving end-to-end network we call DaveNet. Ladies and gentlemen, let's take a look at this.
Oh. Holy cow. Whoa. Whoops. Wrong way. Ooh.
Ladies and gentlemen, DaveNet. Now, you guys, just very quickly, you saw what happened. DaveNet was actually figuring out where to drive when there were no lanes. It made a transition from asphalt to dirt. It was driving in the rain. It was taking curves all by itself. We didn't mathematically figure out how it should turn. It was just simply turning all by itself. After training by us, watching us drive, and all of the conditions by which we detected and the actions that we took, DaveNet now takes something very similar to that. And as we continue to train this network, I believe DaveNet will become superhuman in its driving capabilities. Well, if we want to push the limits of driving, we need to have the right platforms, the right computing platform to do the research. As you know, every computer scientist needs a computing platform, and our scientists needs a platform as well. And one of the things that would be really cool is to have, well, if you have a supercomputer, you really ought to have a supercar. And this supercar is the world's first autonomous race car. The first autonomous race car. It's designed by a great designer named Daniel Simon. It's 2,200 pounds, so it's, as you know, an F1 is about 1,500 pounds without gas. And it's going to be, well, I don't, we'll see how it turns out, how fast it is. But as you know, an electric motor has incredibly fast, high torque. It should be blazing fast. And so this is going to be the world's first autonomous race car. And along with that, if you have a bunch of people who get together to have an autonomous race car, you should have an autonomous race. The world's first autonomous race called RoboRace. 10 teams, 20 identical cars. Every single car has to have exactly the same brain. And the thing that's going to differentiate it is our network. This is going to be differentiated by the creativity of computer scientists as we figure out how to train these cars to go at incredible speeds. This is going to be part of the Formula E season. Ladies and gentlemen, RoboRace. Now that is a great looking computer, huh guys? Okay, that's it. Ladies and gentlemen, GTC 2016, I'm so excited about the work that we're doing together. The buzz is in the air, the air is electric, the environment here, the researchers, all the amazing work that you guys are going to do. We announced 5 things today. We talked about VR, we talked about AI, we talked about self-driving cars. We announced 5 things. The Nvidia SDK, the essential tools for GPU developers. Iray VR, the first rendering capability for photorealistic VR. For designers, for architects, unbelievable tool. Tesla P100, the most advanced GPU ever made. The world's first GPU designed for high-performance computing centers, hyperscale centers. Nvidia DGX-1, a deep learning supercomputer in a box. The most advanced computer ever created, the highest performance single node, 170 teraflops, 250 servers in a box for $129,000. And then lastly, in autonomous cars, HD mapping, and then of course, really, really cool stuff, AI driving. Thank you guys. Have a great GTC 2016.
thanks for watching, guys. Sorry about that. Well, I think we all kind of think AMD is going to be in a very good position very soon. No worries, guys. It's alright for the stream. I hope you enjoyed it. You know, it's still really impressive, some of the stuff they did, but very disappointing, obviously, that that didn't come towards the end. So thanks for watching, guys, and AMD is going to be in a bit of a good position soon. See you guys. Bye.